Welcome to the course of perception algorithms for autonomous systems. We are on the studying tracking. So, to study the tracking, we completed estimation theory, almost everything. We completed the least square estimator, the basics of tracking, classification and sensor fusion we talked about for linear least square, obviously not for nonlinear least square. Then we talked about maximum likelihood, maximum a posteriori. We talked about Kalman filters in details. We talked about the nonlinear Kalman filter, primarily EKF and UKF. This lecture we will be covering something called statistical linearization or unscented Kalman filter. So, I told last class that EKF is a algebraic linearization. So, it approximates your state distribution only one single point, that is your actually mean, and it disregards the probabilistic spread, this probabilistic spread of this error ellipse. Okay, this 2D error ellipse it disregards. So, that is why this is actually your distribution of x. When you calculate now fx, fx is also a nonlinear function. So, your mean is only kind of shifted from here to here, you can see your mean is shifted here, and but your distribution or the orientation of your error ellipse, if you say it is a position velocity or x1, x2, x1, this error ellipse is shifted from here to here, you can see this. So, your major axis, minor axis, eccentricity, everything has changed, orientation, inclination, everything has changed for this ellipse to this ellipse. Okay. So, it is not a very good approximation, it is not a very good approximation. So, that is why to improve the thing, we have there is something in late 90s by Julier and Ullmann, and before that Durant White also was there, and then some other people. They extended a concept called statistical linearization. Statistical linearization means I will be approximating this distribution not only along the mean only, I will generate few more regression points covering my distribution from both extent, my positive extent and my negative extent. So, because your actual x means what? X bar plus root over p into 0, 1. So, mean plus standard deviation or plus minus, I will write the plus, not only plus, plus minus. So, you have to take over. So, positive side also you have to consider, negative side also you have to consider. So, that is why you see there are uniformly distributed points from positive half as well as in the negative half also, okay, because your mean plus minus root over standard deviation. So, that simple thing, if you can remember, UKF is nothing for you. So, this is called something called sigma points. These points along the mean, whatever has been called, these are called sigma points, a specific name, or you can say this is called something weighted regression points. And I will now, once I generate from my x, from my x, if I now generate my sigma points. So, x is my random variable. Now, if I generate my sigma points or this regression points, those points I will pass it through my fx, say lambda I is your this thing. So, I will pass it through fx, and there I will be doing f of xi, I will calculate. So, transformed sigma points to the nonlinear function I will calculate, and then all the so I will have those nonlinear transfer function evaluated each and every sigma points, and when I have now some sample points, I can calculate easily my mean and variance by weighted averaging. You get your mean, and what is the definition of variance? What is the depression over mean? What is the deviation over mean? That is actually your variance. So, you can calculate numerically your mean and variance. So, this is a very simple kind of conform thing. Instead of mean point, your x bar, I will approximate the distribution with few plus side and minus side, few points that will be telling my sigma points, and that number of points we will be deciding later, and we will be doing an weighted averaging of all these points when obviously after passing through the nonlinear function fx, I get xi. So, from let me tell the sequence how it is done. So, you have your state x, you have your variance P. From this you calculated something called sigma points, uniform. One is center point, another one is this thing, using some of this sort of thing. Say I am telling it 2n plus 1, we will tell later. For each now your nonlinear function you evaluate for each of these points. So, 2n plus 1 points will be created. Now, you numerically you calculate averaging what is your mean with certain, obviously with some weight, and you calculate what is the dispersion over mean. So, summation say f of minus this or lambda 0 actually, that is your this thing, minus f of minus lambda 0 transpose for I runs from 1 or to 2n plus 1. Okay. So, this is all actually what UKF does. Actual sampling, well, you can do it even better. So, instead of limited number of points, you sample your distribution for all number of points, because your n01 is kind of random number. You can calculate n number of points in all the direction, not only in this, you can calculate here, 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 and you calculate your actually true mean and true covariance when you transfer it to the nonlinear function. Okay. So, this is the concept of unscented Kalman filter. Those who are working in any kind of thesis in their masters and PhD thing, answer UKF is important for them. Okay. So, I just told the sequence. Already I wrote the sequence here. The same thing now I will explain how UKF is calculated. So, you start, your random number is x, it has a mean x bar and a p, px. So, your first sigma point is your central point, that is the mean. Mean is your state, whatever current state, plus some scale into square root of px, the first column of px. Now, px is what? Actually, when you do px, it is actually having your covariance of x. Okay. So, it is a n cross n matrix. When I do square root of it, we can numerically you can solve it, something called Cholesky decomposition or QR decomposition. These are all very important things. And for doing this, the first and necessary and sufficient condition is P matrix has to be positive definite. So, the determinant of the P has to be greater than 0 and also its minors, the determinant of them should be greater than 0. And this is a bare minimum condition for a Kalman filter to operate. Normally, whenever you do your Kalman filter, if you test your P matrix, your determinant part, if you check, it has to be positive definite. It cannot be positive semi-definite also. If it is positive semi-definite, that means 0. There could be a determinant, it could be 0, and if it could be 0, then you might across a theta singularity in your Kalman gain computation. Okay. So, that is not the case. So, now you operate both side, plus minus, both side you have calculated. When I say, so you did the L plus lambda is just a scalar factor. Well, what is actually now? So, lambda I will tell later. Lambda is a scaling factor which is called alpha into L plus kappa. L is nothing but your number of states. So, it is n. Kappa is just to guarantee positive definiteness of your error variance matrix. So, some positive number greater than 0, you can put 0 also, you can put 1 also, does not matter. Some number you have put. Okay. L I have already told. Alpha is a kind of spread of sigma point variables. Okay. So, what is sigma point variable? So, how much spread you would like to give. So, if you want to, because you do not know this error leaves exactly. So, how much value you would like to give. By empirically, you can took it within 1 e minus 4 to 1. Normally, 1 is good enough. You can check it 1, it will work again. And then you have this P matrix, say 4 cross 4 P matrix. Okay. Now, take each and every either row or column, because P is a symmetric matrix, does not matter whether you take individual row or individual column, same thing. You can take it for column. So, you can take like this for your first sigma point computation. So, suppose you have 4 states. So, that means number of sigma points will be 2 into 4 plus 1, that is 9. Out of 9, 1 is your mean. So, remaining is 4, 4, 8. So, 4 on the positive side and 4 on the negative side of the distribution, right. So, plus 4 I have taken 1, 2, 3, 4, again minus the same 1, 2, 3, 4 x minus this. So, I got total 2n plus 1, that is 9 sigma points here. Okay. Now, when I get the sigma points, I have to calculate its weight also, because I have to do a weighted average, because I will be approximating the distribution based on I have my points available. Now, I calculate mean and variance numerically. That is all the theory is there. So, I calculate my weight for the mean, the central point sigma point, this is the weight, this is for covariance weight, this is for a mean or covariance weight for other numbers. Okay. And this beta, these are all scale factors, these are all tuned and all for optimal this thing. Beta is equal to 2. So, you got now your lot of chi's or sigma i's. Okay. The sigma i's now is passed through your nonlinear mapping. I will use the word mapping. So, this is your nonlinear mapping, okay, nonlinear function. All you pass it up, all you pass it for all the 2n plus 1 sigma points, you pass your 2l plus 1, whatever, n, l, both are same for me. You can pass it up. And once you pass it up, then actually you calculate the mean of this thing number and the variance of this transformed sigma points. You are done. Your prediction is done. Same way you do your estimation as well. So, that is the same thing. So, you have now sigma points like this. This is your central sigma point, this is your positive side sigma point, this is your negative side sigma points. You have put it into a nonlinear distribution. Okay. So, you calculated transformed sigma points after the nonlinear mapping, mapped sigma point basically, nonlinear mapped sigma points. How many? 2n plus 1 you calculated. Now, simple, you do weighted averaging. You already have calculated weight for your mean things, you do it. Similarly, you do the variance calculation. So, dispersion over mean. So, what is the deviation over mean? Okay, that is your variance. So, this is your variance, this is your mean, xk is your mean, whatever x value. Now, each and every sigma points, that is why I have noted it I. I have I is my 8 sigma points, 4 from the positive part, 4 on the negative side in the along your error ellipse here. So, with this I am doing the transpose with my weight, I get my variance. Numerically I am calculating. Okay. So, my predicted values are calculated. Very good. I am very good. I am very happy. Now, I will calculate my predicted measurement. Predicted measurement also now say your measurement function is also say y equal to hx plus b. Your r you have theta and r, range equal to root over x square plus y square, theta equal to arc of tan inverse, arc of tan y by x or tan inverse y by x. Okay. So, here also you do like this. So, again now you have your predicted sigma points, fine, you got your predicted sigma points. Again those predicted sigma points, this xk bar and pk bar. Again what you do? Again you have to do it the same nonlinear mapping, okay, with h function now, with h function. So, again you have to calculate your predicted sigma point. Here these are all estimated sigma points. Now, you have got your predicted distribution. Now, predicted distribution also you have to do sigma point transformation. You have to call the sigma point generator routine and your predicted now sigma points will be calculated. These are all estimated sigma points. These are all predicted sigma points you will calculate. Pass it through your nonlinear H matrix. Same way you calculate its mean, predicted measurement and its your innovation error covariance. This thing or innovation error variance or residual error covariance, whatever you say, you get it like this. This is your output error covariance. Okay, output error covariance is what? Sigma point. So, x, p of x, z. So, p c transpose. Output error covariance is p c transpose or p equal to h transpose. So, this is actually your predicted sigma points from which is simulated from a predicted distribution minus its mean plus the output sigma points which is transformed through your H matrix minus mean, the transpose. Next, these are all your simple Kalman filter equations, there is nothing else. Okay. So, this thing is original Eric 1 or Simon Julier paper. So, that thing is being actually depicted here, but they have used a something called multiplicative uncertainty, because but if you use it with without any loss of generalization, it can be used for additive uncertainty also. So, that when your measurement noise and process noise, instead of multiplicative, it is additive also, there is no problem into it. The same equations can be used. Okay. So, now UKF routine we found. Now, let me just summarize. The summary is very important. So, what we did for so far for UKF? I start with any Kalman filter, I start with estimated distribution at k minus 1. I calculated my predicted, I want to calculate my predicted distribution. How I calculated it? Using the estimated distribution, so that is estimated distribution is this xk minus 1, k minus 1, p of k minus 1, k minus 1. Okay. With this, what I did? Actually, I generated 2n plus 1 regression points, sigma points, the way I told. You call your sigma point generator routine function, it will generate your sigma points for 2n plus 1. You fit one mean, one variance. You transform it, the new sigma points, by passing it through your nonlinear function. Nonlinear function here is your this Markovian dynamics, the state dynamics. You push it there. Okay. Once you push it there, your nonlinear sigma points are evaluated at each estimated sigma points. Got it? Now, I will calculate my predicted sigma points or predicted state and predicted state error covariance. How I will calculate? I got my all these things. So, my predicted sigma points I got it. Now, I will just do some numerical addition, weighted average for calculate my mean, and the dispersion of mean I will calculate, that will give me my variance. So, I got my predicted distribution. Now, from the predicted distribution, now you have predicted points, you have to pass it through your predicted measurement and predicted measurement error covariance. Predicted measurement error covariance means innovation covariance. So, again you have to, so those predicted distribution, predicted points, predicted states, now you have to calculate it another set of sigma points, that are called predicted sigma points, you calculate. So, you have your yk and your the variance. Okay. Now, you transform it to another kind of sigma point calculation. So, this is your actually predicted values and this is your innovation error covariance value, and you calculate your output error covariance. So, once all this thing you calculate, you simply run your Kalman filter measurement update. So, once you update the Kalman filter measurement update, all your Kalman gain, your state update and your this P update, you get the ultimate data. Only problem in this method is that this method is time consuming. So far you are calculating only on mean, be it UKF, be it EKF or be it pseudo measurement filter. You are operating only one point. Now you have to operate with 2n plus 1 point. So you have 4 in your error ellipse, 4 on your upper side and 4 on your lower side, negative side. So each and every state you have now 2n plus 1 vector. So suppose now you have you have 4 states. So you have now 2n plus 1 vectors. Each vector will have your 4 states. So you can imagine the computation is kind of increasing in unscented Kalman filter. Okay. So that is why unscented Kalman filter is not that much kind of used in tracking application. Well, in paper and all, you can definitely use this thing and see how much benefit you are getting when you are doing state estimation over other methods. So that is why EKF and pseudo measurement filter especially are the kind of holding the key in when we start doing the target tracking. Okay. So, with this actually I would like to kind of complete this sort of nonlinear lecture. Before I go to next lecture, I would like to brush up the key points of what we studied in Kalman filters so far, because understanding Kalman filter will be your bread and butter. If we do not understand Kalman filter properly, the next part of a lecture won't be able to understand, because that is the tracking, and tracking is only about understanding the good understanding of a Kalman filter. Okay. So, what is a Kalman filter now? I just want to brush up whatever we have done. So, Kalman filter is kind of a optimal observer. It used to estimate the state of a system from a set of noisy measurements. System state is also modeled is a white Gaussian noise with corrupted with white Gaussian noise, and measurements are also corrupted with white Gaussian noise. Point number 1. Point number 2, Kalman filter operates in linear system only. So, if it is a nonlinear system, we have to do approximations like EKFs, UKF, pseudo measurement filter, all these tricks we have to do. Second thing, third thing is Kalman filter is called linear unbiased estimator, or something, sometimes it is known as blue estimator. Blue means best linear unbiased estimation. So, that means your all the error biases or mean is 0. This estimation error is also 0, prediction error is also 0, your innovation error has to be 0. So, it is bias free. So, this is called unbiased estimator. Okay. And this is, and that property now resonates to your innovation, because actual when you are running tracking, you do not have any truth. You do not have any ground truth available unless you generate the ground truth in a test scenario and all. But if you are getting direct measurement data, you won't have any ground truth. When ground truth is not there, what you do? You normally, you simply what you do? You simply check your innovation, whether your innovation is 0 mean or not. 0 means your Kalman filter is still remaining unbiased, your estimation is proper, and it has to be chi-square distributed with the 95% confidence interval, alpha is 0.05. Okay. So, with this it has to be chi-square distributed, that not only the innovation error squared, the norm of innovation. Norm of innovation also is a very important thing when we study the tracking. This is very important to understand. So, these are all very important points, summary points. So, with this I like to thank you all. Thank you for your time.